Okay, we're going to talk about our combination and permutations and how we use those with our probabilities. So we start off by just defining our factorial. And so factorial for n factorial starts with our number, and then it goes n minus 1, n minus 2, all the way down to 2, 1. So you've seen this before, and we define something where 0 factorial is equal to 1. And we'll see why that's important as we get into combinations and permutations and what that means. So we can simplify these things. If we look at this, you can use a calculator. You have a button on your calculator, but you can do this without it, and you don't really need a calculator. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, and we can see we cancel the 1, 2, 3, 4. We're left with 5 times 6 times 7 times 8, which is a number that we can understand. Right? This on the top is 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9 on the bottom. We cancel everything that we can, and we're left with our numbers on the top, or 4, 5, 6, 7, 8, 9. And again, you could plug it in a calculator and get a number, but for something like the next one, you can't do that. And so I see this goes 1, 2, 3, then times n plus 1, and ends with n plus 2. That's my last value here. On the bottom, 1, 2, 3 times all the way up to n, that is n factorial. So what I'm going to be left with here is n times n plus 1 times n plus 2 on the top. That's my final answer. Same idea on the next one. It goes 1, 2, n minus 2, n minus 1, 1, 2, all the way up to n plus 1. On the bottom, I have my n factorial. Those cancel out. And then this is 1 to n to n plus 2. I cancel out the things that cancel out, and I'm left with 1 over n times n plus 2. And again, you'd be a little bit careful with how you go about it, but writing it out will make the most sense. And we're going to use it mostly on these ideas of permutation. So we have two ways we can count things. One is where the order matters. That's called a permutation. The other is going to be a combination. So one way to remember it is a combination lock is actually incorrectly named, where you have your combination, which you have to put in order. So the combination 2, 4, 5 is a different combination than 5, 4, 2, even though it's the same numbers. And the way this works is if we have two things, we have from n things, we choose r of them. So those are our starting points. So from how many ways can 10 people be placed first, second, and third? So I have 10 people. My number of choices are 10 times 9 times 8. Right? I select the first person, then the second, then the third. I can't have the first person be the second place winner as well. And so that's 10 factorial over 7 factorial over 10 factorial over 10 minus 3. So if you simplified stuff like this, you come to this formula. And what that is n is my total number of things, which in this case is 10, and r is what I'm choosing, which is 3. So one way you talk about it is from n pick r, and that will be your permutation. Alright, so here's some examples. Again, we're talking about arrangement, so order matters, which makes it a permutation. I have 6 books, and then I'm going to choose, I'm going to pick, right, how many? Well, I'm going to pick all 6. And so I get 6 factorial over 6 minus 6 factorial. And here's where our 0 factorial comes into play, where we define it to be 1. And so I just get 6 factorial on the top. That's the way that I can arrange them. There's 720 ways that would work. All right? For the next one, I have 5 of the 6 books arranged. So from the 6, I'm picking 5. And again, I just plug through my permutation, and I get the same answer as we move through this. Because basically, once you've picked 5, you are implicitly picking the 6 because you have only one book left. So it's the same ordering as we'd have for all 6 books. On our next piece here, we have 6 history books, 4 math, and 3 science. And how many ways can the books be arranged on a shelf? All right, so again, be a little bit careful about how this would work. But you think about from there's 13 books, I want to pick 13 of them, right? And I just select from there 13 factorial is around, 6 billion. So there's a lot of ways it could work. You could think about this other one differently, but if they have to be grouped by subject, right? History has 6 ways that it can be grouped, right? From 6, pick 6. Math is going to have 4, pick 4, 4 factorial. Science is going to be 3, pick 3. Now we have to think about how many ways can those be grouped. So I could do history, math, science, science, math, history. I can think about how those are going to work. So the number of choices, right? 6 factorial, 4 factorial, 3 factorial. That would be one way to order it, right? And then I'd have to deal with the different ways that could look. And so from the 3, pick 3, that's 3 factorial. There's 6 ways that that could look. So it's 6 times that whole thing is my final answer as we are ordering those by subject. Okay. Again, this is if we have our permutations. So if we have things that are the same, so we have P that are alike and Q that are alike, we just divide out that that repetition. And we also have a circular arrangement where we take the factorial and then we divide by the number of things, which is just n minus 1 factorial. So we do a couple examples like that. So we have circle and repetition. And so the key with the circle is that we have no defined start, which is why we could basically, we divide by the number of things in that circle. So if I look at 7 kids, 3 of them are the same clothes, so we're just going to assume they are the same, and they're not the same person. So it's n factorial over p factorial, which is 7 factorial over 3 factorial, and 3 is the number of triplets. And I get 7 times 6 times 5 times 4 when I divide out the 3 times 2 times 1. If we think about it, right, each triplet, if we put them in some place, right, we don't know where they are, but let's just say they're right there, we could switch them, right, for any set, we'd be able to change them in terms of our order. So it would be an identical set to have T1 and T2 switch, or T2 and T3. There's 6 ways that that could work from the 3, pick 3, and we're just really dividing by that number down here on the bottom. And so that's where our values come from, of just 7 over 3 factorial when we work through it. In terms of calculus, so we have to worry about repetition. I wouldn't be able to tell any difference between those 2 C's had they been switched, and the 2 L's and the 2 U's. So I just did the same thing, which is my 8 factorial, because there's 8 letters, and then I divide out the repetition, which is 2 factorial, 2 factorial, 2 factorial, because I could switch the C and the C, or the L and the L, or the U and the U, and it would look the same in terms of the word. And so that's my final answer in terms of the ways that you could arrange that. So again, these are unique situations where you have repetition or you have a circle. And again, here's our circular thing. We have 8 kids divided by 8 because we could rotate that spot. In a line, right, those 8 spots would look like that. There's my 8 people. In a circle, right, I wouldn't be able to tell who's at the beginning of that. It could be P1, it could be P2, it could be P3, right? So basically this one ordering would be overcounted 8 times if we put it in a circle, right? We could basically wrap it around here where P1 holds P8's hand, and I would have to worry about those as long as P1 and P8 are next to each other, right, it would be the same ordering. So we just divide out those pieces. That would be the same circle. They're still holding the same hands as we move through it. So we'd have that 8 times. That's where the division by the number of things comes through if we were to do it all the way out. All right. So we just divide it out. Again, it's easier probably to remember the formula, but the formula makes sense. You can derive it if you need to. All right. So 5 different model houses in a cul-de-sac would be our circular arrangement. Can be arranged. All right. 5 divided by 5. 5 factorial divided by 5 gives us 24. All right. We have 11 stars on a soccer team, filled the 11 spots. Again, the order is important from all 11. You pick 11. You have 11 factorial different restrictions on who plays what position. All right. On the second piece, if the starting positions are selected at random, what's the probability that keeper Kendra is chosen to be goalie and either scoring Sally or choker Chelsea is chosen to be the center forward? Well, this one might be easier to list stuff out. So I want to look at the possibilities, right? Possible outcomes over total number of outcomes. So I have 11, pick 11 is my total. And then on the top, think about what you have in each position, right? So for the goalkeeper, I have one choice, and that is Kendra. For the forward, I have 2 choices, right? That's Sally or Chelsea. And those are my 2 values. And then for the rest of them, I'd have to worry about. But this is not right? In terms of, we got to think about how that would work for our other values. Okay, so I have the other 9 positions to fill. So I have my choices, 1 and 2, just like before, but now I'd have 9, 8, 7, 6, 5, all the way down, right? And so really what matters is that all that the restriction is on these points on the goalkeeper and the forward, I could still fill the rest of the team lots of different ways, and that's going to be my final probability as we finish it up. So that's how it works with our permutations. Right? We can also have combinations where the order is not important. So where just the group, the final group, is important. And this looks very similar to our permutation, and it is, if we covered up that r squared, that is our permutation. Basically, we just take out the repetition. So we take out how many ways those one groups could be put together. So that's our permutation. You divide out the number of ways that the subgroup could be arranged. So you're basically taking out the order, which makes it the combination, and then you go from there. So I have how many ways could 25 students be selected to leave class early? It doesn't matter if you're the first person or the fifth person chosen, right? Just that you're part of that group. So from the 25 over this, and then we have to divide out the way that those 5 could be grouped, and that will give us our final piece. So a group of 5 could be 5 pick 5, which is 5 factorial, and that's what we divide through, which gives us our combination formula. And that would be our final answer. All right. Look at the next one. How many ways can 5 students be selected? If the first will leave 5 minutes early, the second 4, so on and so forth. This is now the order is important. If you get picked first, you're 5 minutes. If you get picked second, you're 4 minutes. So being picked first and second is not the same as it was up here. And so now we have to worry about using a permutation, no longer a combination. So if we do this, we'd plug through our numbers, right? And you get your values, which would be there. So again, you just have in terms of your permutation. We can do some more examples, right? And the probability, that's different, is you need the total number of outcomes. So we get our selected values, and then you get your total number of outcomes. And so let's say that we have a co-ed croquet team. We want 4 boys and 8 girls. And then we can take 7 team members in a van. The rest will have to go in a car. Right? The students get the minivan at random. What's the probability they'll have 2 boys and 5 girls? So we think about, we have 12 total, right? The order is not important. I just pick 7 people to go in the van. It doesn't matter if you're first or 7th, right? You just get in the van. And so from the 12, choose 7, right? There is that number that I could have total. That's my total sample space. Okay? So that's how many ways I could just get 7 people from the 12. Now, from this, I want to fit the boys and the girls. From the 4, I could choose 2 boys, right? And from the girls, from the 8, I could choose 5. Those are the ways I could get my boys and girls together. And so I get a number, right? So my probability is 36 over 792. Using the combinations with my just the division for the probabilities, right? All girls, if we look through this, from the 8 choose 7, right? Okay, from the 8 choose 7, I get a value of 8. That's over my same sample space, because that's all the different ways that I could get 7 people from the 12. All boys, from 4 choose 7, right? I can't get 7 things from 4, so there's no way, there's no probability, or there's a 0% chance, 0 probability that I would get all boys. More boys than girls. We have to list out all the different ways that could work. So that could be 4 boys and 3 girls, right? So 4 choose 4, 8 choose 3. I get my numbers, and that's out of our sample space of 792, right? That the 2 brothers are in the van. So there's 2 choices for that. Then there's 5 other spots, okay? And so from the 10, choose 5. I get those values, and so my probability, again, is over the same sample space. So again, this is really tricky, but if you just think it through on this level first, think of your combinations and how it works together and plug through it, you'll be easier to get your answers in the end. Don't try to get to this number at the beginning. Break it down into the ways it could look, and then from there, apply combinations or permutations depending on order, and that'll get you to your final answer.